unit, make sure that you're practicing questions to apply the information. So just thinking that, I understand it and that's it, that's not enough. Make sure that you're trying to explain it to someone, practicing a few questions, and just really building up your test taking skills as well, which is looking at questions, being able to deduce or reword the question in terms of clarifying what the question is asking, and then thinking about your responses and then looking at your answers. So get really comfortable doing that process. That's going to help you on your exams as well, and kind of build up your question momentum, if you will, or your test taking skills. Okay. All right, so we're moving on to the second part of membrane transport. And so our first objective here is to identify the 3 general factors that influence the rate at which substances can be passively transported across a membrane. And then we'll speak about the 2 general factors that influence the rate of active transport, okay? And so really this objective has to do with how fast particles are moving across the membrane. So we know the forces that are moving particles, right? We spent some time describing that in the first packet. Now we're going to talk about how that can be modified or regulated. How can we speed that up? How can we make, the rate of transport kind of go faster? And so there are some factors having to do with the cell, having to do with the cell membrane, having to do with properties of that particle, of that solute, whatever it is in question, that would help to increase the rate of that transport. And so the first thing we want to describe as a part of understanding that is diffusional equilibrium. Diffusional equilibrium is a state where there's no net transfer of molecules, okay? And so if we look at our first part of this illustration, we can see that side 1 has an equal concentration, an equal amount of particles dissolved here as side 2, so it's equal. And so there's no net direction of movement on either side, okay? Where there may be one-way flux, and one-way flux means we may have 1 or 2 particles moving from one side to the other, but the solutions are here at equilibrium. There's no net flux on either side. And so that's diffusional equilibrium, all right? Now in scenario B, we see net movement, right? So we have a higher concentration of particles dissolved in the side 1, a lower concentration of particles dissolved in side 2. And so now we have a gradient for movement. So we see net movement happening from side 1 to side 2. In other words, from higher solute concentration to lower solute concentration, okay? But this is where we kind of like to be. And so particles are going to move like this in this second illustration until they get to this state, which is what we refer to as diffusional equilibrium. And remember, in diffusional equilibrium, we may have particles still moving, but there is no net accumulation on either side, okay? Because we no longer have a gradient. Now, just to review here, passive transport, we said is spontaneous. We said it does not require energy, and we said it's a downhill motion or downhill movement. There are 3 types of passive transport. So simple diffusion, facilitated diffusion, and diffusion through channels, okay? So remember, although we can have different modes of passive transport, the general theme is that it's particles moving according to their concentration gradient. They're moving downhill. They're sort of moving with the flow. This is spontaneous. This could happen simply, and simply means that they're just going right through the membrane. This could happen in a facilitated diffusion way where they're using some type of transporter, but they're still moving according to a gradient. And then we can also have diffusion through channels, again, requiring some type of facilitation, but it's still according to the concentration gradient. In other words, that downhill passive movement. Now, the characteristics of simple diffusion is that there's no membrane proteins required, there's no transporters required, there's no channels required. These particles can go right through that lipid bilayer. And as you would imagine, only some specific particles have the ability to do that. We talked about that when we talked about the structure of the lipid bilayer. So it would have to be a particle that is small enough, that is uncharged, that is non-polar, in other words, hydrophobic, in order for it to go through that lipid bilayer, okay? Some of the factors that affect the rate, in other words, how fast these particles can go through that lipid bilayer, are going to be the magnitude of the driving force. So to what extent do we have a concentration gradient? Are there a lot of particles on one side and a little bit of particles on the other side? Or are the particles closer in their concentrations, right? So the magnitude of the driving force, how big that driving force is one thing that will affect how fast those particles will move through the membrane. The second factor is the membrane surface area. How much surface area exists for transport? How much exposed surface area is there? And if we have twice the amount of surface area, we're going to see twice the rate of simple diffusion. Okay. And then the third factor is the membrane permeability. So how likely is that particle to go through the membrane in the first place, right? How accommodating is the membrane to that particle? If the membrane is really permeable to a particle, we're going to have a faster rate of simple diffusion. If the membrane is not so permeable to the molecule, we're going to have a slower rate of diffusion. And if the membrane is impermeable to the solute, we're going to have no movement, right? No simple diffusion. Okay, so let's illustrate that here a bit. Oops, and then we'll keep going. So we're looking at simple diffusion, and let's first make a note of these factors. So the magnitude of the driving force is what determines the rate of simple diffusion. Actually, let's put in brackets here. So the factors that determine the rate of simple diffusion. The first one is the magnitude of the driving force. And just to really clarify and specify here, this is the chemical driving force, right? Based upon the different concentration gradient of that particle. Okay. The second factor is the permeability of the membrane. And then the third factor is the surface area available. For transport. Okay. And so let's illustrate that here with 3 cells and 3 scenarios here. So we got cell A, cell B, cell C, and separating these cells, let's just pretend that there is a membrane here. Okay. And we've also got some amount of particles dissolved on either side here. So in scenario A, we've got a lot more particles dissolved on the first side and no particles dissolved here. So let's say 1 molar versus an osmolarity of 0 molar. In other words, no particles dissolved. So pure water, okay? In scenario B, we have a smaller difference between our concentrations, okay? So let's say we have 0.8 moles of particles dissolved here. And on this side, we've got slightly less. Let's say we've got 0.5 moles of particles dissolved. And then in scenario C, we have an equal concentration of particles dissolved. So 0.5 mole. And then on the other side, the exact same amount of particles. Okay. Excuse me. So what we'll see here is that for scenario A, for this cell, we're going to see a really strong chemical driving force, a really strong driving force, moving particles from one side to the other, okay? And we want to bear in mind that the membrane must be permeable to the solute in question, okay? So let's make that note. The membrane must be permeable to the solute in question. In other words, as long as the membrane is permeable here, we're going to see a faster rate of movement or a faster rate of diffusion through this membrane because we have a stronger difference. We have a stronger chemical driving force, okay? So a strong chemical driving force equals a faster rate of simple diffusion. In scenario B, we don't have as much of a driving force because we don't have as strong or as a large of a concentration gradient, right? The amount of particles are pretty close. They're not as drastic as we see in scenario A. And so we do have a driving force that wants to move these particles, but it is a smaller driving force, okay? Again, bearing in mind that the membrane is permeable to the solute. So in scenario B, we have a medium or intermediate. We have a medium chemical driving force, which equals a medium rate of simple diffusion, okay? And then in scenario C or cell C, we actually only see one-way flux. So we've got flux this way, we've got flux that way, so we may have particles kind of bouncing from side to side, but there is no net accumulation, okay, because our concentrations are at equilibrium. So we don't have a driving force, so there's no CDF because there's no concentration gradient. And so the rate is 0, right? So the rate of simple diffusion equals 0. And we can say here that the particles are at diffusional equilibrium. Okay. And so this really just highlights that first factor that increases the rate. The fact that if we have a big gradient, a lot of particles on one side and no particles on the other side, we have a faster rate because we have a stronger force. If we have no gradient, we have no movement because we have no force, okay? And if we have a sort of intermediate gradient, we have an intermediate movement because, intermediate rate, excuse me, because we have an intermediate force. Okay, and then the other two forces also hold true. The other two factors also hold true. There must be permeability. In other words, the particle must be able to go through the membrane. If the membrane is really permeable to this particle, we're going to have a faster rate as well. And then the third factor is the surface area available for transport. And that makes sense. If I had this one cell, let's say this was the only surface area available for transport, I would have a medium rate of movement of particles. But let's say I double the membrane here. Let's say I extended the membrane such that there was twice as much surface area available for movement of particles. I would also double my rate of simple diffusion. I would have faster movement of those particles if I have more surface area available for exchange. Okay. Okay. And so what we can see here is that the first factor is the concentration gradient. And so as big as the concentration gradient can get, that's as fast as we're going to see the movement of particles. The bigger the gradient, the faster the movement. Okay, so that's a directly proportional relationship, which is being illustrated by this graph. As the concentration gradient increases, the net flux, the net accumulation, that net movement of particles will too increase. Okay. The second factor is the membrane surface area. Again, if we have more surface area exposed, we're going to have more movement of particles. And a really good example of that is in the alveoli of our lungs. And so what we're seeing on the left is normal, healthy lung tissue, where we have a lot of alveoli. We have a lot of surface area available for exchange of gases. Think about carbon dioxide being diffused out into the environment. Think about oxygen being diffused in. And so if we have a lot of surface area, as we do in this normal image of the lungs, then we're going to have more of an efficient amount of exchange of those gases. On the right, we're seeing what happens when there are collapsed alveoli, which happens with lung damage. And so we can see that there's less surface area available for exchange of those gases. And this is why we see hypoxia and cyanosis, which is bluing of the nails and bluing of the mucous membranes, because there's not enough oxygen being diffused to circulate the body. And so that happens because we've lost some of the surface area for that gas exchange to take place. So more surface area equal more exchange, faster rate of exchange. Less surface area equals a slower rate of exchange, which can become detrimental in some of our exchange surfaces in the body. Okay, and then the third factor is the membrane permeability. How easy is it for that particle to get through the membrane? How much does the membrane facilitate movement of that particle? And so membrane permeability is in turn influenced by some other factors as well. So the lipid solubility of the diffusing particle or substance. In other words, is this particle lipophilic, hydrophobic, or is it hydrophilic, lipophobic? Okay, how easy is it for that particle to get through the lipid bilayer? If it's a fat soluble particle like cholesterol, like our steroid hormones are, even oxygen and carbon dioxide, these are nice lipid soluble particles that can go right through the membrane. If they're not lipid soluble, if they are hydrophilic or lipophobic, okay, if they're polar, they're not going to go through the membrane, and so that's going to affect the permeability there. The second factor affecting the permeability is the size and shape of that particle. When we talk about big, bulky particles, think about big, bulky proteins or glucose. These are not going to be able to get through the membrane. They're just too big. They're just too bulky. They're going to need some other type of mechanism. That's where we're going to get into transporters and so on. Okay. The third factor is the temperature of the environment. Now, this is not as relevant in our physiology because of homeostasis, because of the fact that our temperature is relatively stable, but this can be a problem in terms of extracellular scenarios, okay? So if we increase the temperature, we're gonna have more movement of particles, okay? More movement of those particles is gonna translate to faster rate of diffusion, all right? And then lastly here, the thickness of the membrane. So again, if the membrane is a thick area, we're not going to see optimal exchange. This is why it's so important for our exchange surfaces of the body, like the alveoli, need to be really thin membranes in order to facilitate that exchange. If we have more membrane, we have more stuff in the way, and it's harder for particles to go through.